Okay, well, let's go ahead and get started. We're going to continue our study of cache systems. We're going to get through the middle part of it, which I think, in my opinion, is going to be the most important part to understand for your midterm and your finals when they come up.
Oh, that does exist, doesn't it?
Yeah, they do exist.
After spring break.
After spring break.
Is it a Monday after? Or?
We'll make it the Wednesday after.
Okay.
Yeah, if we make it the Monday, that would just be mean, right?
Yeah.
Yeah, that's just mean.
Can we have a review day?
On that Monday.
Sure, I'll
Yeah.
review for 10 minutes.
Yes.
And then
Perfect.
we'll finish up on caching.
You know what those remind me of?
All right, so
Rainbows?
why do we have caches?
It's fast.
It's fast. Okay, so fast. What? That's right. So it's for performance reasons. What are they speeding up?
Retrieval from memory?
Yeah, retrieval from memory. Now, why is this a problem?
Because
memory
people are
retrieval is
impatient.
slow.
People are impatient, right?
It takes forever trying to retrieve stuff.
Yeah. So main memory takes forever, and so we want, and it's big and slow. So we want something that's small and fast, and we want to try and keep everything inside the cache so we can access it quickly. So we went through this example last time. We're going to go through it again just to make sure it's clear what's going on. Oh wait, I did not use those markers. There we go.
Yay, nice marker.
All right, so notice we have two cache lines, 1, 2, or actually 0, 1.
Yay.
We have a tag, which is telling us which memory address we are storing, and then the data is the actual byte of memory. And what does the V mean?
If you've accessed it or not.
Close.
Valid?
Valid, right. Is this line valid or is it invalid? Okay. So when we start, what do we do with the cache? We,
Check validation.
well, we invalidate all the lines.
Check it.
Yeah, because there's nothing in there yet. Memory has whatever.
Yet.
All right, so we're loading from memory 1. What do we do? Or what does the computer do first?
Check
It's
memory
in the
one.
cache.
Yes, is it in the cache?
No.
So it is a
Invalid.
miss.
Miss.
So it's cache
Misfire.
miss. No valid tags, misfire. It's a cache miss. So what do we do now that we have a cache miss?
Check memory.
Well, we don't have to
you,
check.
You store the tag, right? Tag
Yeah,
one.
you store the tag in there. Put the tag right there.
Check
and-
memory. Then take the data from
And
memory, put it in there,
Yep.
and then you store it into R. No, you do the
Revalidate.
You validate it, right.
change that to
And then you store it into register 1. Everyone got that?
Yee.
All right.
I like the arrow.
because it's one. Wait, it's one, right? You just put it into
How'd you
one.
put it into
register
register
one.
Register 0. We had to put it into 1. You usually initialize it to just start at the beginning.
Doesn't matter.
Good job. All right, LRU, what does that mean?
That's that's the eviction notice, you know.
Oh, he's the eviction notice. I liked it. Yeah, eviction notice, least recently used. He's the one that's going to be evicted. So I like that. It's the eviction notice on this cache line. You're next to be evicted. I like it. That's good.
You said it last time.
I did? Oh, well, I'm glad that stuck. I'm amazing. All right, 5. What happens?
Same thing.
Yeah, so it's a cache miss. We pull number 5, but it's not the line 0, it's line 1 because that's LRU, aka the one with the eviction notice. So we put 5 in the tag, bring in the data over, validate the tag, or the cache line, sorry, validate the cache line, and then move the 150 over into register 2. Great. Now why is line 0 having the eviction notice, or LRU?
Because it
Because it wasn't the last recently used.
Yeah, he's the least recently used, not last recently used, which
Yeah.
would actually be that
So
kid.
he wasn't the last.
Right, so
recently
he's the
used.
least furthest back. Because if you had multiple cache lines, you want the furthest one back.
Right.
The one that you haven't used recently. So
Correct.
You don't screw up your stuff.
Least recently, yeah.
Least
So, you do a reference to 1, what happens?
It's there.
It's there, so it's a cache
Hit.
hit. All right, we have hit because it's in there.
Sunk by pouch.
Great. We send it over, and then who's LRU now?
So the second
And
one.
the next one, yeah.
We
So,
made a comment last time.
now we're going to read from 7. What happens?
Not in there.
It's not in there, so it's a cache
Miss.
miss. All right, good, everyone's following. All right, who gets evicted?
The least recently used.
Yeah, 5. So he has the eviction notice. We change the tag to 7, read in the 170, move the 170 over there. We don't have to update validate because it's already valid. And then what happens to LRU?
Goes back to the other one.
Goes back to the other one. Great. Then we try and read from 7 again, and we have hit. Awesome.
So, why didn't you use the 0 one instead of?
Oh, you mean register 0?
Yeah.
This is just an example. Yeah, just to show you how it's working.
He just didn't like 0.
Who likes
All right, 3 misses, 2 hits.
Ta-da.
All right, any questions on this example? We did it last time, but I want to make sure this is clear because we're going to be doing this a lot today. Good morning. All right, how do we calculate the average access latency? Well, it's the cache latency times the hit rate of the cache, and then for our architecture, it's then the miss rate times the main memory latency, because we only have a single cache and a main memory. We don't have anything in between. So we're going to say that well, it looks like for ours, there's 1 cycle for a cache, and we'll say it's 15 for main memory. That 15 would be much higher in real life. Good morning, Jonah.
Here's his lateness.
So 2 out of 5. So yeah, no, 40% of the time we hit the cache. 60% of the time we hit the main memory. You math it out, aka arithmetic. We need about 9.4 cycles per reference. How could we improve the latency?
Change the hardware.
Yeah, we could try and make memory go faster. That's probably not going to happen. We can improve the cache access latency. Well, it's down to 1 cycle. I don't know if we could really change that much more. Or we can improve the cache hit rate, because that would move more of the hits to 1 cycle as opposed to 15. So we need to find out. You gonna be okay?
She's not.
We need to come up with different tools to improve the cache hit rate, because we want as much to be in there, in as much as many. Let's rephrase that. We want as many cache hits as possible, right? We want, whenever we access something, we want it to be in the cache.
Yeah.
Yeah. All right, there's a visualization tool if you want to see it. Great.
If you want to see it.
Let's do a class problem. For a given application running on our MIPS32 single cycle data path that we've talked about and y'all are all going to implement perfectly in Lab 5.
Sure.
You measure that 40% of the operations are access memory. So 40% access memory. You also measure that 90% of memory references hit the cache. Oh, great. Whenever a cache miss occurs, the processor is stalled for 20 cycles to transfer the block into memory. So the instruction takes 21 cycles. What is the cycles per instruction for application X on this processor? Okay, let me tell you how you approach this. First, you need to figure out how many are memory references and how many are not. Well, how many operations are not memory references? 60%. So you have 0.6 for 60%, and you need to multiply it by how many cycles that takes. In our single cycle data path, how many cycles does an instruction take? 1, because we just wait for the whole thing to complete before we go to the next one. In more advanced architectures, they're going to take a varying amount. But for now, it only takes 1. That's great.
Easy math.
But, bless you.
Easy math.
So now we have this 40%, right? And we got to figure out what's going to happen here. So for the last 40%, you measure 90% of those references hit the cache. So that is 0.4 times 0.9 times how many? How long does a cycle or instruction take if it hits the cache? 1. So we're gonna have 1. But we still have our 0.4 times 0.1, which is the last 10% of the caches, which takes 21 cycles.
20. Is it 21 or? Yeah, 21.
Takes 21 cycles. Stalls for 20, and then takes another cycle. All right, who's the calculator? Do it quick.
Phone.
There it is.
It's 0.4
Wait, 96 plus.
Yeah, so 0.9. Wait, I don't know why I lost my
0.96.
ability to do math. All of a sudden, I sure did. Yeah, 96 plus.
0.84.
What does that equal? Hmm?
Maybe 1.8.
1.8,
Yeah, what? Oh, yeah. Okay. Well, that's pretty good. Even though we have a slow main memory, it didn't quite double the speed. What would be the CPI if there was no cache? Well, 0.6 times 1 plus 0.4 times what?
21.
Yeah, 21. What does that equal?
0.6 plus something.
That'd be 9. Be 9.
9.
Sure.
0.6 plus 8.4.
Oh, yeah.
Is that a small difference or a big difference?
Different.
Big.
Difference. Wow. So the cache is making a huge difference here.
Yeah.
Yeah. All right. Now, calculating the actual cost. These are what, storage? Yeah, storage requirements. So it's 2 bytes of SRAM. You have 2 4-bit tags. Now this is the cost of our cache, namely, how much does this guy cost space-wise to put in there? 2 bytes of SRAM, so plus you need the tags, which are 2 4-bit tags for our system, because we only have, what is it, 16 total bytes of memory. Not a very big memory, but that's what we were doing. The cost of the tags is unfortunately forgotten for caches, but this drives the cost of the side. What is the cost of if a 32-bit address is used? Well, let me look at this real quick. You get 2 bytes of SRAM, 2 4-bit tags, which is really 8 bytes. So this would in total take, how many bytes?
10.
3.
No,
3.
different.
3. 4 bit.
Oh,
4 bits.
Yep.
A bit is a nibble. 2 nibbles equal a byte.
24 bits.
So it would be, yeah, it'd be 3 bytes. Yeah, 24 bits in total.
Yeah.
What if it was a 32-bit address? How many bits are in the tag?
32.
32. 2 times that is 8 bytes, so it would be 8 bytes plus, which would be 10. So it's 3. You got 3 bytes up here, and you got 10 bytes down here. What's
Oh,
this?
squeaky.
Nice and squeaky, thanks. So the tag can take a significant amount of your space, is the point here. Do y'all see? Because if no one has a 2-byte cache. You usually have a 64-byte cache or 64 kilobyte cache or something. Well, if you just increased it from 4 bits, aka half a byte, to 4 bytes each, multiply that by 64, things just got huge for what is supposed to be small. So the point here is we want to try and somehow make it so that the cache tags are a lot smaller, so it's easier to work with, consumes less space, and therefore is faster. Because small is fast, big is slow.
Yeah.
Yeah. How to reduce the overhead? Well, we can have a small address. We could just say, all right, you can only access 16 bytes, but that's not very practical, since we want to access at least 2 to the 32 different bytes, aka 4 billion bytes. Also, caches are supposed to be non-architectural, aka when you write your program, you don't write your program thinking about the cache initially. You don't want to be doing that. You just want to write your program and make it work. So, terrible idea. Cache bigger units in bytes, so each block is a single tag, and blocks can be whatever size we choose. Okay, this actually turns out to be a good thing. Let me see if they give you a good picture. Oh, good. So now your cache line, instead of having 1 block, is going to have 2 blocks. So this cache line is going to have 2 blocks in it, and this cache line is going to have 2 blocks as well. Notice that the tag field just went from 4 bytes to 3 bytes. Why did that happen? Well, let's look at an example, and I think it'll help you. All right, we initialize everything to 0. What's going to happen when we try and read in memory 1? It's going to be a miss. So it's a miss. Whoops, hold on. Yeah, we'll go and show you. It's a miss. Notice that the address is in binary. The address in binary is 0001. The tag is only the first 3 bits. So it's going to store 001. And the block, this bit over here is the block offset. How far you're going to jump down the block, down the cache line in order to find the data. So when it's a miss, you're actually bringing in 2 different bytes into the cache at this time. And then the block offset tells you which byte you want to retrieve back. Now, you may think this doubles the amount of time it takes to go to memory and back. It ends up not being the case because the way main memory works is it has a very wide bus and can send you many bytes at once. It just takes the same amount of time. In other words, when it's sending you 1 byte, 2 bytes, or in reality it's more like 128 bits or bytes as well. Yeah, it's very wide, yes.
So because the tag now only has 3 bits, it stores both of the options for what the last bit would be.
Yes. Yeah, that's the way to think about it, yeah. And that last bit, if the last bit was 0, it's just this guy, but it's the offset. You know, you start here and you jump by the offset. And that's how, in here you only have an offset of 1, so you can either have 0 or 1. Okay, great. So, read in 1, that's great. And then we're going to go down to 5. Is that a hit or a miss? All right, who gets evicted?
No.
Yeah, the bottom one. Again, the address of 5, you write 5 in binary. 4 plus 1 is 5, 0, 1, 0, 1. That is the block offset. I don't know why that arrow is going up there. It should be down there. 0, 1 stored in the tag. Okay. Other one gets the eviction notice.
Where is the block offset stored?
It's not stored anywhere. That is the trick. And it'll make a lot of sense right here. Notice when you go back to read 1, you don't store the block offset. You take the address, because this is memory requesting byte at 0001, in binary. It goes to find the tag, which is just the first 3 bits. It's in the cache, and then it uses those last bits of the address to find out which block it needs to go to, and then read it back.
Got it.
All right, good. So this is a hit. It's a hit because the tag is in the cache, and then we just use the block offset to figure out which byte we need.
Okay.
All right. Why does the other one get the eviction notice?
Because I was the least used.
Yep. All right, so we're going to read in 4. 4 is a hit, but we never read memory address 4 before, but it ends up being a hit. Why is this the case?
Because it was part of a 5.
It was part of 5, right. This ends up being actually not only decreases our tag size, but actually increases our hit rate as well, because we're pulling in more data that's probably going to be read as well. Because you think about it, if you're most of the time you're using small arrays for things. So if you're pulling in large chunks of data that's close to each other, you're probably going to access the data around it. So this is actually a very real life case where you did one memory reference and the next one, which you haven't read before, ends up being a hit because we stored it in the cache. Yeah. So that's a hit, great. And then 0, well that's a hit too, even though we never read from it because beforehand we read 1.
What happened to the second one?
After the tag in the second one, so 0, 1.
Oh yeah, that's interesting. Huh. Yeah, ignore that.
Got it.
Okay. You see how this is helping with our tags and actually increasing our hit rate?
Yes.
So do you change the tag to 4's binary when you?
Wait, to 4 is binary?
Yeah. So like during like the previous call.
Oh, no, you didn't change the tag. Because
Okay,
when
so
you
you just
requested
kept
that,
the 5.
remember, If it was 5, it'd be 0, 1, 0, 1.
Okay, so-
But the tag is just this part.
Yeah, so it's the same.
We don't care. It's the same tag for both of them. They just have a separate offset. Okay. Great. Any questions on this? This is the first big performance improvement for caches. Hmm? Nope. Okay. This is called spatial locality. Notice, as I pointed out, when we accessed address 1, you also brought in 0. It turned out to be a good thing because we referenced 0 later on. This is called taking advantage of spatial locality, which says that if you reference a memory location, we are more likely to reference a location near it than some random location. Probably because we deal with a lot of small arrays. Or when you also have, you bring in an object, like a student object, that's stored in a contiguous piece of memory, so chances are you're going to access those fields that are close to it as well. So it ends up being a very good thing for performance.
I assume the blocks are bigger than 2 in real life.
Yeah, the block size is usually, what is it, 8 or 16? If the block size was, I call it 2 or 4, I will say, then you just wouldn't have this tag down here. You just store one tag and you store the 4 bytes right there.
Yeah.
Right. Yeah. Now, can you, no, this is a cybersecurity question. If our block size was really long, how could this be a problem from a cybersecurity standpoint? This is actually what happens in Meltdown. Wow! My video's not up.
Have you not been capturing?
Oh, I've been capturing.
Oh.
Yeah, I just didn't put the video up.
Not the video.
Couldn't it potentially be because somebody might only have like access to certain information, but because of how much it pulls, you pull too much?
Yep.
That's right. Awesome.
Yeah, think about it. They only have clearance for the first couple, but it takes in everything.
They could
You
have
need
access.
everything.
You could have access to everything else. Nice line.
Nice.
That is so even. There we go. That's a little bit better.
And the lines totally stayed in the box.
Whatever, it's a
That
tag.
is really small.
The computer does that.
Any other complaints? Comments? Screams?
Just put
It
0.
Alright.
screams.
There you go. That makes me happy.
Yeah.
This is gonna be so tiny.
There we go.
Let's say user process. And you all are somewhat familiar with process, right? Different programs run on your machine, right, Carla? Are you okay with that, Carla? You sure? Okay, good. I'm sorry.
You eating a Halo?
Bless you.
There you go.
Are you eating a Halo?
All right, let's say the user process is mapped to right here.
Yeah.
All right, and let's just say because this is main memory.
Okay.
We good?
Yeah.
All right. Let's say your SSL program is stored, I don't know, we'll say right next to it.
Uh-oh.
And we'll just say that your key is stored right at the edge. If I put in an access for this block, which mapped to right here, where's
Good
the key?
access everything.
The keys in the
The
gap.
key is maybe right there. Is that a good thing or a bad thing?
A bad thing.
It's
Way
bad.
bad.
Way bad.
Well,
Now,
it's good for the person who's trying to get it.
Yeah.
now,
That makes it easier for them.
Yeah.
now. Normally this is not, you cannot exploit this because in hardware
Most
they
people
put
don't
a
know.
memory detection bit right here, so that if you're a user program and you try and access this cache line, even though I brought it into the cache, you can't access it because the memory bit is on. What Meltdown and Spectre are going to do is they're going to get around that protection, but we'll get to that later.
At
So
another time.
you see how we've started setting up a security issue? Yeah. Okay.
Teach me.
Teach me the ways.
Teach me how to get around it.
Teach me, everyone.
Teach me how to tear down people's infrastructure.
Yeah. Yeah. All right. Okay. Doing great.
Force.
Use the force. Yeah. To get to that, we have to do a lot of other things, but at least we've started to
We
build.
can actually use the force.
Yeah, we can use the force. Okay. So back to spatial locality. We've talked briefly. What's that?
So if the force is holding somebody's company hostage.
Okay. So how do we determine the block size? How do we what's the best way to determine how big the block size should be?
Math.
Math? No. Math is actually terrible. A
Aw.
terrible,
Make it the biggest
terrible,
block size possible.
Thank you.
terrible solution for this.
Aw.
Make it the biggest block size possible. No, because then it takes too long to access things and bring them in.
That sounds like
Yeah,
a
you're
personal problem.
Okay, good start. You take a guess, and then what do you do?
You see like how long it takes.
Okay, and then
Adjust
it.
accordingly.
adjust accordingly. Thank you, Jonah. You're a perfect architect. How do we do it? We simulate a lot of different block sizes
Lots of testing.
and see which one gives the best performance. Yes, that is literally what we do.
Test.
We just make a simulator
Nice.
and we get some benchmarks and we just keep running a bunch of different numbers until we find.
That's what my
The maximum.
process is gonna
That's
be.
why I don't like this.
That's why what?
That's why I don't like this. I
Oh.
don't like testing.
That's what my
That's
job
right.
is.
No,
Oh,
this
you're
isn't
gonna
testing,
never-
this is simulation. It's
You're
different.
simulating your tests, though.
Simulate? No, there's no
Still-
tests. We have benchmarks and we're simulating the benchmarks and trying to figure out what numbers match up the best.
You're still plugging
But
in
we're not
different
testing to make
numbers.
sure it's correct.
No, you're still plugging in different numbers and seeing what happens.
Yeah, but you can also write a program that does that for you automatically.
Automatically. Oh.
That's what my job is gonna be this summer.
Most systems use a block size between 32 and 128 bytes. So those aren't bits, those are actual bytes, which is actually a pretty significant amount.
Yikes.
But it ends up being that main memory on some systems can transfer 128 bytes of memory in one, I'll just say transfer. So that's fine.
It's just like, here you go.
Longer sizes reduce the cam overhead by reducing the number of cams and reducing the size of each cam. All right, what am I talking about here? Well, this whole, what?
The tag.
Thanks. If this whole thing, why do I write above that? Let me write below it.
I don't know.
Come on, Jonah, help me out.
I'm
man.
sorry.
Failing me. If this whole thing is 32 bits, and the block offset is 32, our blocks are going to hold 32 bytes. What's the block offset? How many bits are in it?
How many bits are 32 bytes?
256.
No.
No. What?
Right, I know this is kind of confusing. The block size is 32, so each of these blocks over here are going to be 32 bytes in length. So the block offset needs to reference 32 bytes. How do we reference from 0 to 31?
5 bits.
5 bits. So in this case, it'd be 5 bits, which means our tag is going to be what?
Minus 5?
Yeah, 27.
27.
Yeah,
27,
so this
yeah.
would be 27. Now, on the other hand, if the block offset was 128 bytes, if the block size was 128 bytes, whew, that was bad. The block size was 128 bytes, what would the block offset be? How many bits would that be?
Oh. That times 4.
7.
7.
Seven.
Jason.
100 bits.
Which would make the tag what?
121.
32
Oh.
minus 7,
Oh, JK.
25 bits.
Oh, I thought we moved.
I thought it was minusing from 128.
Yeah.
Oh, no, oh.
Yeah.
You
see.
confused us.
Okay. I think you confused yourselves. I stand by my statement.
We did 32 bytes. It was 5 bits.
5 bits, because that's how many.
128 is 7, so is that like power of 2?
Yeah, these are all powers of 2s. So, when you increase the block size, you decrease the tag. Y'all see that?
Mhm.
Why do we want to decrease tag? It reduces the number of comparisons we have to do, number of CAM lookups, which reduces the size of each CAM, which makes your cache actually faster
Yay.
and consume less area, so you can actually store a larger cache as well.
Yay.
So you want to increase the block offset at least as much as you can, but if you go past a certain amount, then you have to do many transfers from main memory, and then it slows the whole thing down. So there's kind of an upper limit to it, and also you might be pulling in too much data and pushing other data out as well with your block.
Find the happy
Offset.
medium.
Yeah, and how do we find the happy medium?
Testing.
Testing.
Simulation.
Let's use the word simulate, because testing means something completely different. We simulate it and find out. What's that?
Nothing.
Come on, Jonah, loud and proud.
I said simulate.
You did. Thank you, Jonah.
That's fine.
All right, class problem. I
Oh.
love. Yeah. I
Right.
love class
Oh
problems.
no.
You're having fun with these today.
Oh well, yeah. They're pictures, right? We get to do it in a diagram. Okay.
Very colorful diagram.
A very colorful diagram. All right. Oh, peg plus cat. You know it? No. Okay, good.
What?
What?
Hype cat? You said? Hype-
Peg plus cat? Oh, it's a little kids show, and it's all about math. And one of the episodes was all about let's do it in a
I
diagram.
was just going with the song. It's filmed,
Why do you say
know,
such mean things?
I did not say that.
Oh, you did that?
That was
Why do you
not
say
me.
such mean things?
Ouch.
You
That was
gotta
not me.
admit you know I do that, so
I do.
you can't act offended.
What's up with that girl? All right, who's doing it? Let's go.
Yes.
I'll do
We
it.
will help. All right.
But I'm gonna eat my apple at the same time.
Okay. And then let me do this marker for you. There you go. You're welcome. I'm gonna sit back here.
Okay. Well, it's obviously a miss for the first one, but these also get set to 0. And then you you load 7, so this would the tag for 6 be 100?
100, correct, yes.
Yeah.
Okay.
And then
So
what gets?
then you get 160 and 170,
Yep.
and the offset's 1.
So you.
You store it. Oh wait, yeah. It's
There you
one
go.
anyway.
All right.
And to change that to a 1 now.
All right.
Okay. And then we go on to the next one,
Mm-hmm.
and it's another miss. No wait, it's a
No,
hit.
that's a miss.
That's a
Yeah.
hit. 'Cause it's there.
Yeah.
And that goes into this one. And
You're done.
that's all I do.
Yeah.
Here to this one, and that one's a miss. And I put it here.
Because he has the eviction or the LRU eviction notice.
Right. And hit 9.
So you need to be
So I do
101.
101.
Yes.
And 180 and 190. Now it's on. And that one goes to 3. And I'm done with that one. And this is another miss. And it goes here because this one's the LRU,
All right. So he gets evicted.
right?
You know what? Yep. You want to get the eraser. Mark, you get the eraser.
And this one, would it be 110
Yes.
to access it?
Wait.
To get
One.
these two?
Yeah. Hold on. Brain stop. Yeah. You're
Here.
correct.
Then how would you access these two?
Hold on a second. 1. Yep. It's not 110. It's 1. Hold on. Okay. Wait. How do we write 10? It's 101. And wait. Hold on. Our 9 is wrong.
Yeah.
It should be 100 for our second one. There we go.
And my first one was
Yeah.
wrong too then.
Yeah, it's
No.
okay.
No, the first one I think was right. Because 1000 is the 8, and then 1001 is the 9.
No, I was talking
so
about
that's
these
correct.
two.
Yes.
'Cause I think I did
six
those
is
two as
wrong.
Yeah,
one,
she
zero,
did those
zero.
two as 100.
So those two
Oh,
should
yeah,
have been.
alright, but it still was hits and misses correctly. We just had the wrong tag written.
Right.
It's okay. Let's keep
Yeah.
going.
Okay.
Should have been 0, 1,
0, 1.
Yeah, exactly.
So this one should be 101.
Yes, 101. That makes sense.
Alright. And we got 200. 10.
Mhm.
And right over register 3. 200. And I'll move to here. And it's 11, which we accessed here, so it's a hit. And it gets put in new register 2. And 210 goes here.
All right, great.
You have to move the LRU though.
Yeah, yeah, and of course,
Yeah.
here's the LRU. Well, I don't know, portable LRUs. There we go.
It looks like this is Lou.
Good old Lou.
Was your camera actually recording that at all?
No.
No.
Okay,
No.
yeah, you're right.
Too bad
I thought it
people.
was-
Well, if I change the recording, it it's gonna.
It disappears.
It looks like this. Well, it's even worse. It looks like that, which means nothing.
I can't wait to see that. It looks like this.
Okay. All right. Everyone got this?
Yes.
All right, great.
You're gonna have to
So,
do that on the exam.
I have one question,
Yes.
because obviously I got confused with the tags. How do
So
you like?
the problem was is 7 is actually 0111, right?
Mhm.
And then this is the tag
Okay,
that goes up here.
so it's based on a 4-bit, and you take.
We currently have 4-bit addresses,
Okay.
right?
Okay, that was my mistake. I didn't think about it in that manner.
Yeah.
I thought that the tag was 3 bits, and that you were trying to base it on those 3 bits.
Yeah, but it's the first 3 bits, not the second.
Right.
Or
so I
the
got-
second set of bits. Okay,
Yeah.
let me pause the recording now because we